All right, so we might as well get started. Hopefully, I'm hoping to get through the bandit section today because I'd like to move along and see how we're going to apply these. So, yeah, we introduced the bandit setting last time, and we mainly were talking about different objectives, and the first objective was this pack objective, which I'm not going to go through in detail, but it was a big, long definition. And it had this probably approximately correct aspect to it. And we talked about, why do we have an approximately? And that's because in theory, if your arms are arbitrarily close to one another, you would have to have an arbitrary number of samples to actually distinguish them. So you can never really guarantee that you're going to get the best arm, but you would like to be able to guarantee that you get close to the best arm. That's the approximately. And the probably was, well, regardless of your problem, there's always a chance that your algorithm will be unlucky and fail because you could have a coin that you flip 1,000,000 times, and every time it's heads, even though it's a fair coin. So there's always a non-zero probability of something like that happening. So that's where the probably comes in. So probably approximately correct. We went through the definition and we said the simplest algorithm you could come up with is to pull each arm W times, average the results, and return the arm with the best average. So that's really simple algorithm. And the only point of introducing it was to see whether it was a pack algorithm, whether we could show it's a pack algorithm. And we did by showing how to bound the value of W so that you can get a guarantee. And at the end of all that, I'm not going to go through it again, we found that, yes, it is a pack algorithm. If W is greater than this quantity here, K is the number of arms, this was your probably, this is how much you want to guarantee the algorithm won't fail. So the smaller this is, the more reliable you're going to have the algorithm run. And epsilon is how accurate you want it to be. How close do you want it to be to an optimal arm? And so W is going to grow as epsilon becomes small. You want to be more accurate, and as delta becomes small. And it's also going to grow with the number of arms, as you'd expect. So as long as that's true, then we're going to return something that's close to the best arm. So that was the main point. And if we look at the total number of arm pulls, that's going to be K arms times W per arm, and that gives you this quantity here. And so this is a polynomial number of arm pulls that meets the pack guarantee, so it's an efficient pack algorithm. That's the main result. And we ended last time with the question of, can we do better than this? Right? So it seems like the most straightforward basic algorithm you could come up with, pull each arm the same number of times. We went through the analysis. It gives us what we want, but can you do better? That's the next question that a theoretician will ask. And so does the uniform algorithm seem good to you? Like, how would you try to do better if I told you that you can do better? How would you go about that, maybe? What's inefficient about it, or what seems inefficient about it? Right, I've got 10 arms in front of you, and you're going to sit there and you're going to pull each one the same number of times.
Mm-hmm. Actually, we care about the optimal one, but we're actually distributing our sample size equally to everybody, even knowing that somebody may be suboptimal. Mm-hmm. So maybe we should. This is more on the explore side. Maybe we can combine the exploit side. So once we see some candidates, could be optimal, we just focus more on the energy of them.
Okay, so try to exploit a little bit more, right? Anybody have anything to add to that? That could be dangerous too, right? If you exploit and somehow this really good arm looked bad in the beginning. But that's definitely some intuition. I mean, if there's a really, really bad arm compared to the others, do you think you'll need many polls to identify that as a bad arm? Right? If this one has like an average reward of 0.1 and this one has an average reward of 10, it's not going to take many polls to figure that out. And you'll never figure it out with 100% probability, but with high reliability. And so if you figure that out with a small number of polls, then you might as well just eliminate it, right? And focus on the others. So that's sort of the idea of, that's how you make these things more efficient. You try to exploit information you've gathered so far to be smarter about how you allocate arm polls. And uniform doesn't do that, right? It doesn't even look at it doesn't even look at the outcomes till the very end. So that's what basically we're saying here. You want to do some non-uniform sampling with the intuition that there are going to be close calls between arms, and you're not going to be able to necessarily distinguish between them early on. But the really big differences you can probably distinguish with a small number of polls. And so that's where this algorithm called median elimination comes in. This is sort of the first theoretically optimal in terms of number of polls algorithm. And it's a very simple one. So we're, these, I'll show you what the formula is for WI on the next slide, but we'll ignore that for now. So there's some function WI, and basically this is going to be organized in rounds. So on round, and I is our index on the round. So round 1, we're going to pull each arm. We start with our set A that contains all the arms. We're going to pull each of them WI times. So that's like our uniform algorithm, right? And then we're going to compute the median of their average rewards, and we're going to eliminate half of the arms, okay, the ones that perform below the median. And then we're going to, and we eliminate them by removing them from A. And if at that point A has size 1, then we're going to return that arm. Otherwise, we're going to go to the next round, and we're going to pull each arm in our set, the remaining set, WI times. And WI is going to tend to increase over time, just so you can get some sense there. And then you're going to eliminate half the arms then, based on their average reward. And then you're going to keep on doing this until you get down to one arm. And so, how many rounds roughly are we going to have to go through, like in the worst, at max? Log, right? So it's going to be log number of arms rounds, basically every time, ignoring the sort of rounding effects. So this kind of makes sense, right? And the question is, how do you pick these WIs, right? Because we want to pick the WI so that at the end, when you return this arm A, it meets the PAT guarantee. With probability delta, it's approximately optimal. It's within epsilon of optimal. And so that's what this paper is all about. How do you derive what value the WIs should have each round? And we're not going to go through that because it's a little more complicated. This is all math that you could follow, but it just takes a while to go through. And so this is the formulas they use, and we can at least look at them qualitatively. So WI is going to be based on EI and epsilon I and delta I, and you can see this is a form that we kind of saw in the original PAC algorithm. And over time, you're going to make the deltas. So on round I, as I increases, the deltas are going to get smaller and smaller. So you're going to try to get more and more reliability. And here you see they actually get exponentially smaller, which seems bad, but the deltas are inside a log, so it doesn't kill you. And the epsilons also get smaller by some factor each time, right? And so basically they just try to make the reliability more and more, because as you eliminate arms, you're getting arms that are sort of closer and closer to one another, right? At the end, you might have two arms that are very, very similar, and then to distinguish between similar things, you need more polls. So if you do all of the analysis, like you figure out, you do all the math, and given this, you could figure out the total number of poles by looking at how many times you go through the loop, which is log k. If you do all that, you find that the number of poles is order k over epsilon squared, log 1 over epsilon, log over delta. And that's similar to the uniform bandit, but you don't have this log k factor. And so it's a small improvement, but it actually turns out that this is the best you can do. So this is sort of theoretically optimal. They show that in the paper as well. And yeah, that's so basically any other algorithm that does better is going to have to do better in terms of constant factors. And yeah, but theoretically it's not really interesting at that point. All right, so that sort of finishes the pack objective. There are some other algorithms, but these are the main two that are worth looking at. Like the simplest one and then the theoretically optimal one. So this objective is a little awkward to apply in practice. So it's kind of interesting in theory, but in practice you're usually not going to be able to say, here's my epsilon and delta. And usually in practice, even if you were able to say that, the number of poles would be too large anyway for you to actually do, right? Because that's what I always say. These theoretical results are always they always have to handle the worst case. And so for that reason, they're always going to be larger than you want. That's just a fact of life. But they can often drive you to good intuition. And you can run the algorithms anyway with larger values, but that's just the fact of life. So and also the pack objective. Sometimes you're not given a budget on arm poles, and sometimes you can't control how many arm poles you have. Like the pack objective, it wants to tell you how many arm poles to give it, and sometimes that's just not our setting. So this is going to be awkward to work with in a lot of cases. And so to get something that's a little more, that's easier to use in practice, in objective, we're going to look at two others. One's cumulative regret and one's simple regret. So we're going to move on to our second objective now, which is cumulative regret. And this is the one that's sort of most similar to what was originally proposed in the 60s when they introduced the multi-arm bandit. It's sort of inspired by the medical trials, where you want to sort of, throughout the trial, you want to make sure you're getting the maximum benefit for everybody in the trial and thereafter. So here, we want to have an arm pulling strategy so the expected total reward at time step n is close to the best possible, right? And so we're looking at the total reward we get up to a time n, and we want to have a strategy that's close to, what would be the best strategy if you were omniscient and you knew everything about the bandit? What strategy would have the best expected total reward if I let you know everything about the bandit? What would you do? Yeah, just the arm with the highest expected reward, you would just pull that n times. And the expected reward for that would be n times the expected reward for that arm. So that's the best you could do. And the cumulative regret objective is to try to get as close to that as we can after n pulls. Okay? And in particular, they want to quantify what is the regret at each step. Where the regret, we'll look at the math in a second. The regret is just after n pulls, how much worse am I than if I had known the optimal arm to begin with? Right? That's why they call it regret. It's the regret for not knowing sort of the ground truth. When you're running a bandit algorithm, you're trying to discover that over time. All right, so we can talk about, for this objective, you know at least one algorithm that's really simple, the uniform arm pull algorithm. So you could modify the uniform algorithm so that you just do a round robin, right? You basically pull each arm after another, and you just keep going around. So roughly, they're all getting an equal number of pulls. So would that be a good strategy for this subjective cumulative regret? Do you think? What do we think? No? Okay, so we've got some no's. Another no. Would it be a good strategy? Why wouldn't it be a good strategy? Anybody over here? Like we're pulling each arm roughly an equal number of times. Why is that not a good thing if we care about maximizing the cumulative regret? Any ideas?
If you're maximizing the cumulative reward, would you want to go with the gold orbit and not the bit?
You'd like to get more reward, right?
Yeah.
And so what does the uniform strategy do? It just gets reward equally distributed across the arms, right? So I've got two arms here, and I'm going to pull them equally. I'm just going to keep pulling them, and they'll get equal numbers of pulls. But if I figure out that this arm is giving me more reward, I should probably focus more on it, right? Does that make sense? So this uniform arm selection strategy, where you're pulling each one about the same number of times, is very bad for cumulative regret, because you're basically going to get the average. Like if you look at your long-term, the expected value of this strategy, it's sort of the average of the expected values of the arms. It converges to the average instead of the max, which is what we want it to converge to. So that's sort of the point. Uniform is completely exploratory. It doesn't try to exploit, but for regret, we need to exploit. All right, so that's what this says. We've got to balance exploring the machines to find a good payoff, but also exploiting it to actually get a good, to eventually converge to a good payoff in the limit. So let's look at this in more detail. So the theoretical results are usually about the expected cumulative regret. That's all you can really talk about, because any particular run could be arbitrarily bad or good. But we're interested in the expected behavior, just like we are in MDPs. So we're going to have a protocol, which is at time step n, the algorithm picks an arm. And it picks an arm AN based on what it's seen so far, and it receives the reward RN by pulling that arm. Okay, and that's the protocol. And note that AN and RN are random variables, right? Because the arm pulling strategy could depend on the rewards that you've seen so far, and those are all randomized. And so that's why AN can be random as well. But RN we know is a random variable because, well, even if you pick a particular arm every time, it's a random reward anyway. Bandit problems without random payoffs are not very interesting, right? You just pull each bandit once, and you know what they give you, and you're done. So the cumulative regret, expected cumulative regret, which we're going to write like this, regret n, so this is after n pulls, is this. So n times r star is the reward of the maximum arm. So this is the expected cumulative reward if you pull the best arm every time. And the regret is that minus the rewards of the arms that we actually pulled. Okay? The expected the expected values of the rewards we're going to get at each time step. All right? And so this, these quantities, this Rn variable, that depends on the arm pulling strategy. And as we said, if you use a uniform arm pulling strategy, this thing is going to converge to the average of all the expected values of the arms. And you're going to have a constant regret over time, right? Because this is going to be less than this always. And what we're interested in is algorithms where ideally what are called no regret algorithms. So you want an algorithm that eventually will converge to something that has zero regret, right? Because even in the beginning for small n, you're going to have some regret, right? Because the first time you pull an arm, you don't know what the optimal one is. You have no information. But as n gets large, you're hoping that the regret will get smaller and smaller. And so this whole theory is about, the original theory in the 60s, they started out trying to analyze the asymptotic regret. And they show, there are strategies that are asymptotically optimal. And it's only somewhat recently that they analyzed the finite time regret in terms of n. And there you're interested in the rate that the regret decreases. And we'll look at that here. So that was, so this, as I said, it's somewhat recent. The finite time analysis of these multi-arm bandits, they were introduced in the 60s, but nobody really did a finite time analysis, or either didn't think about it or didn't know how to do it until these folks came around. And the algorithm turns out to be extremely simple. It's something called the UCB algorithm for upper confidence bound. Some of you may have heard of this. Some of you may have heard of the UCT algorithm, which is for tree search. Popular, but not my favorite algorithm for tree search. But it was derived from the UCB algorithm. We'll talk about that. So the upper confidence bound algorithm is very simple. And so what you're going to do is A indexes an arm. And so at any time you've pulled the arms some number of times, like each arm has some number of pulls, and that's going to be remembered by this variable NA. So you're going to keep track of how many times you've pulled each arm, and you're also going to keep track of the average reward that you've seen from each arm so far, right? And what we're going to do is then at time step n, we're going to pull the following arm. We're going to pull an arm that maximizes this expression. Right? We'll talk about this in a minute, what this means. And this all assumes that the rewards are bounded in 0, 1. If not, if your bound is like r here, instead of 1, you're going to have an r squared in front, but we'll ignore that for the moment. So we're thinking 0, 1 right now. And so it's a very simple algorithm, right? You just have to keep track of two things for every arm, the number of pulls and the average reward so far. And then you plug it into this expression and find the arm that maximizes it. So we can look at what that expression is. And it has terms that correspond to exploitation and exploration. Right? So first, let's look at the exploitation term. You can just think of this as a Q value, like an average Q value. So how good has this action looked so far? And if an action has looked really, really good, well, that kind of gives it a boost, right? And we'll be more inclined to choose it. If it's really, really bad, we're going to be less inclined to choose it compared to others. But that's not it, right? If we only had Q, like what could go wrong if we only had Q here and did not have this term? Like what would go wrong, do you think? Yeah, you would, it's just like reinforcement learning. If you don't explore, you're just going to get stuck, right? Whatever happened to look good the first time you pulled it is going to be what you pull forever. So this would just be exploitation. So this term is the exploration term, right? And so it's worthwhile to look at what happens here. So n is the total number of pulls, right, so far. And if we, so basically what happens is as you pull an arm more, as A is pulled more, this term gets smaller, right? And if you keep on pulling it, it will go to 0. and there's no exploration bonus for that arm. So you sort of look at this term as an exploration bonus, right? This is how good it looks right now, but this is a little bonus. And let's say for an arm A, let's say you don't pull it. We're just going to stop pulling it for a long time. What happens to this term for arm A? Right, we're going to pull a whole bunch of other arms. Does it grow? It grows, right? As you're pulling other arms, N is getting larger, and the exploration bonus for arm A is getting larger and larger. And eventually, like for any arm, is it always the case that eventually we'll pull it if we follow this strategy? Like, could you stop pulling an arm forever with this strategy? Yes, no? I've got no's. So why is it impossible to like just stop pulling a particular arm forever? Here.
You can prove by contradiction, say that like your QA is how much less than the optimals for now, but eventually as n grows, it's like that term will outperform that difference. So though you will pull this arm very infrequently, but eventually you're going to pull.
Right. So eventually this log n term will get arbitrarily large, right? And so you'll have to pull arm A, right? So if you don't pull arm A, this is a constant. Eventually log n will get so large that this will be the max. So regardless of what QA is. So you're always going to pull every arm infinitely often. But there's a log n here in the numerator, and log n grows quite slowly, right, compared to n. And so one pull of an arm could sort of, counteract the log n pretty quickly. So a small number of pulls of an arm can sort of make this not very significant. But that's the thing to realize. You're always going to pull every arm infinitely often. It's just the arms that are not looking as promising, you're going to pull less often as time goes on. And so again, the math in this paper is not complicated at all. It's just all pretty, just from if you know, the turnoff bound is the only thing that you might not have learned in high school. But it's a long paper, but it's not complicated. We're not going to go through the details here. But the main result that they have that sort of implies the final result is, so the expected number of arm pulls for a suboptimal arm A is bounded by this quantity. Right? So this is, as you run the algorithm for n steps, it's saying this is sort of the number of arm pulls you're going to get for a particular arm. It's bounded by this quantity, which is log n. And then here we have this delta A, which is how suboptimal that arm is, right? And so if an arm is really suboptimal, in other words, its expected reward compared to the optimal reward is large, like 1, then this is going to be let's see, suboptimality. Is this right? So suboptimality. So small. So arms that are closer. Yeah. So when this is small. Yeah. So that's right. So arms that are closer to optimal, you're going to pull them more, right? Because this is going to be smaller, and so that's how this works. But the key thing is this log n, right? It's order log n, and so suboptimal arms are only going to be pulled on the order of log n within n steps. Does that make sense? So that's not many times. And so if you add up all of those log n pulls roughly for all the k arm, for all the k minus 1 arms, suboptimal arms, all the other pulls are going to go to the optimal arm, right? So k times log n is not much compared to n as n gets large. And so that's why this algorithm works well for cumulative regret. It doesn't waste time on suboptimal arms. And putting that all together, you can show that the regret is bounded by log n. So that's pretty strong bound, right? So the regret is basically how fast do we basically converge to essentially having prior knowledge about the best arm, and it converges at a rate of log n. Yes.
In the previous slide, they designed the algorithm, right? So what's the point of 2 there?
That just comes out of the math. This 2 here. Yeah, so the math basically, this is, so the way this actually works is this is an upper confidence bound. So at time step n, they're computing an upper confidence bound on the expected value of that arm. And that's just, the 2 just comes out of the turnoff bound in this case.
Seems like the algorithm would work around the same even if there was not a 2 there, or the arguments are still valid, right?
Well, it wouldn't be an upper confidence bound using their techniques in that case. So yeah, that, you know, we'd have to go in and look exactly where that 2 comes from, but I would guess you can't just remove it and still have an upper confidence bound. Yeah. So yeah, they're you know, these bounds do end up with constants. You know, so for example, here we have an 8. Where'd that come from? It came from somewhere. And it's true, you might be able to improve on those constants, you know, with tighter analysis. This case, I'm not sure, but this was a straightforward upper confidence bound. That's why it has its name. So it kind of makes sense, right? So what are we doing? This is an upper confidence bound on the expected value of arm A. And this algorithm is saying, I'm going to pull the arm that has the highest expected the highest upper confidence bound. And that's all it does. And if you pull an arm enough times and it's not looking as good as your upper confidence bound said, that bound's going to get smaller and smaller. And eventually you're going to pull something else. All right? Okay, so yeah, so is this good? You know, log n, you know, the way you want to think about this, is this a good regret? It's actually a good regret because the average regret per step is this cumulative regret over n, and this goes to 0, right? Pretty quickly. Log n over n goes to 0 very quickly, and so that's why people like sublinear no regret algorithms. So they like this bound to be sublinear, because then your average per step regret goes to 0. All right, and you can also show that no algorithm can do better than log n, like up to constant factors. So this is an optimal algorithm for the finite time case, which is pretty interesting, right? For any value of n, this has that property. Every other result before that was asymptotic. It only sort of held for asymptotically large values of n. All right. So so UCB is good if we care about cumulative regret. So this is something you might use in a some sort of trial or advertising situation where cumulative regret in advertising is you're interested in total revenue, right? Total number of clicks, and so that's sort of the appropriate thing. There are times when you don't care about the cumulative regret necessarily, and you really just care about identifying the best arm as quickly as possible. That's another setting, and that's something that's often referred to as a simple regret, and we'll talk about that. So the protocol here is a little bit different, but pretty similar. So at time step n, our algorithm is going to pick an exploration arm, AN, and this is just like before, and we're going to actually pull that arm. And then we're going to see the reward. And we're also going to pick, we're going to output an index, JN, that the algorithm says is best or thinks is best at that time. Okay, so the algorithm's always outputting two things. It's outputting an arm to pull and its best guess about what the best arm is, which basically you can think of as if you stop the algorithm now and you had to choose an arm, that's the one you would choose. Okay. So the expected regret formula is given by this. So R star is the reward of the best arm, and at time step n, this is what we would predict to be the best arm AJN, and this is its expected reward. And so the difference between these two is the expected simple regret. Okay? Does that make sense? All right. And notice these all have expectations. It's a little annoying, but you have to work with them because this is all randomized algorithms, and you can't say anything like with probability 1. So we're always working with expectations here. So we could ask about UCB for simple regret. Right. Do you think UCB will do something non-trivial for simple regret? Does UCB seem to be identifying the best arm at some level? Seems to be, right? I mean, because eventually you're going to be pulling that best arm most of the time. So it has identified it to some degree. It's not clear that UCB is necessarily optimal, though, for the simple regret objective. But we could say that UCB does seem to be identifying the best arm, and it wouldn't be crazy to try to run it for this situation, right? So if you were running UCB to find the best arm, you would use that to select the exploration arm, and then at any step, what would you output as your best guess for the arm, for the best arm? Right? So UCB had, right, if we looked at the equation, so UCB would pick the exploration arm according to this. Now at time step n, if we asked UCB to give us, what do you think the best arm is, like in expectation, which arm would we return? Would you say something? Right. So you just return the arm that has the maximum QA, right? Because you don't care about this. Like in reinforcement learning, when we're actually, after we've done our learning with exploration, and we're just interested in using the policy, we don't keep exploration turned on. We'll usually turn it off and run the policy. So it's the same principle here. So, UCB could work, but it also you could also say that it puts too much emphasis on pulling the best arm, because UCB has to sort of its sequence of rewards has to converge to sort of the optimal average reward that you could get, and so it has to put a lot of emphasis on the best arm. But maybe it could use some other polling strategies to do a little bit better if all we cared about is identifying the best arm, right? So if all you care about is identifying the best arm, you don't care so much how much reward you're accumulating during exploration, right? Whereas UCB, it cares about how much reward it's accumulating during exploration as well. And so simple regret is just, I'm going to explore, and then I get to output the best arm, and I don't care about the reward during exploration. And really, this is actually the setting that reinforcement learning is often used in, right? You can explore for a while, and all you care about is having a good policy at the end. You don't care about the rewards you accumulate during learning, although sometimes reinforcement learning is talked about that way. But it's just an artifact that during learning you're probably going to be accumulating more reward, but you're not trying to maximize the reward during learning. So that's not how we evaluate the algorithms usually. We evaluate them after they've learned and how well they do then. So I'll go through this quickly because it's not terribly, there are papers that go through all these details, but you can bound the simple regret of UCB, and it looks something like this. So it's n to the negative c for some constant. So as n grows, the regret goes to 0. It's sublinear. Is that good or bad? Well, it turns out to be it's okay, but you can do much better than that in theory. And yeah, I mean, this is one of those weird situations where the stupidest algorithm seems to do better in theory than UCB. So this is all analyzed in this this paper here. There is a better algorithm that we'll talk about, which I would recommend for this objective. But this is the uniform algorithm, right? This is the round robin algorithm. It's just pulling each arm in sequence over and over and over, and returning when you're asked, returning the index of the arm. So it's very much like the uniform pack algorithm, except you can stop it at any time and just ask what arm has the best expected reward, best average reward. And this little algorithm has the regret, the simple regret, grows like this or decreases like this. So it's an exponential in n, as opposed to UCB had a polynomial in n. So, this is theory and in practice. I used to have a homework where people would implement these and look, and you roughly see something like this, depending on the bandit problem. So uniform tends to be a little better than UCB, and they have some theory about that. But there were some later papers that look into other strategies. Another simple strategy that you've seen already is epsilon greedy, right? So with probability epsilon, you pull a random arm, otherwise you pull the greedy arm. And that actually, theoretically, for the simple regret, seems to be better than the uniform as well. And so basically it has the same sort of bound here, but for epsilon 0.5, that seems like a large exploration rate. We wouldn't use that in reinforcement learning, but here it makes a little more sense. For epsilon 0.5, the constant they get is better for this algorithm. And you can show that this in practice it works pretty well as well. I found as well. So if we put everything together, what we have is we had our pack objective. These are the two algorithms we looked at. They were slightly more complex versions of each other. Cumulative regret, uniform was bad, right? Because it's going to converge to the average of all the slot machines there instead of the one that's the best. And UCB, you'll hear about this algorithm a lot. And the reason I talk about simple regret is because I see people applying UCB in places where simple regret is what they actually care about, and it never makes sense. This happens to be the case for the UCT algorithm as well. So people hear about this UCB algorithm for bandits. They get a bandit problem and they just apply it without thinking about their objective. And so it's good to know whether you care about cumulative regret or simple regret. I've tended to find that the 0.5 greedy algorithm is pretty good for the simple regret objective. So very simple. 0.5% of the time, half the time you pull a random arm, half the time you pull the best arm. And that works pretty well. So if you're doing simple regret, don't. I recommend not using UCB. Always keep that in mind. So any questions about the basic bandit material? So we're to the end of that, and so that, as I said, in your own research, you might come across bandit problems, and this is a nice. So you can always come back to this and see what bandit algorithm should I use. You can have references because if you just state 0.5 greedy as your algorithm, they'll say, oh, that's just a ad hoc heuristic. But now you can point to a paper and say, hey, this is even better than UCB. So it gives you a little bit of power there. All right, so next time, just a little preview. We're going to take a little another step toward full Monte Carlo algorithms, and we're going to talk about the idea of Monte Carlo planning for policy improvement. And so we're going to now be in the framework of full MDPs, but we're going to be in a setting where somebody gives you a policy. You know, maybe this is you're in a networking application, and they have policies for networking, for dropping packets, for example. And there's all kinds of policies for this. They give you this, and you also have a simulator. Can you use that simulator with the policy to get a policy that's better than the one that you got? And that's what we're going to be talking about next time. And then after that, we'll move to the full sort of tree search Monte Carlo planning for the full optimal planning problem. All right, so I'll see you on Friday, I guess. Yeah.